So let's continue on here with our next section for electrostatics. Today we're kind of covering two sections in one, but the second section is really just the change in potential energy. So if I teach you potential energy, the change in it is really just final minus initial. It makes sense just to put them both together. These PowerPoints are going to be slightly different than what is written on your notes in the package. So if at some point there's a slide that isn't next in the package, just let me know. I think I know where the different breaks are, but just to make sure. So these two are actually different. This is why electrostatics can be tricky, because we've got electric force, we've got electric field, we've got electric potential, we've got electric potential energy. All four of those are different. So at the very end, I've got a nice little chart that's going to show all four of them and how they're all different, so you can relate between them. So first, electric potential energy. You know what potential energy is. Okay? If I've got two charges, doesn't matter if they're positively or negatively charged, if I put them together, they're going to interact. Either it's going to be pushed or attracted. So it's similar to gravitational potential energy. If I have something up here, it has the potential to fall. So if I've got some point charges, they have the potential to move based on what those charges are. So that's essentially what potential energy is. It's going to look very similar to your gravitational potential energy, as many of our stuff here depends or looks a lot like gravity. So this is non-uniform, meaning it is not the same everywhere. So the further away you are, your electric field changes. Tomorrow, is it tomorrow? Maybe tomorrow? Yeah, tomorrow I'll talk about a uniform electric field. But everything we're talking about so far is not uniform, meaning it changes depending on where you are. You still ran that out? Okay. I can hop back later if you want. So we can derive an equation for electric potential energy. So this is an equation you know. We saw this before. Force electric equals the... what is this? Force electric equals energy potential. There should be, its original form is force is equal to this EP over D. We've looked at what force electric is. That doesn't change. The D here is the same as R. We saw that with gravitational fields. It's the same thing here. The D and the R are the same. So therefore, here is our equation for electric potential energy. Again, this looks basically the exact same as gravitational potential energy, except here it's positive, and I'm dealing with charges instead of masses. But it looks the exact same. Instead of it, before we had EP equals capital G, M1, M2 over R, and it was negative. Now I've got K's and Q's. But it's very, very similar. So in this case, notice where we set our 0 point. So instead of our 0 point being at infinity, like gravity, the 0 point is at the center of the charge. So we're going back to a normal placement of the 0 point.
Can we use the formula as well?
Yeah, that one works too. Yeah, you might have a case where you're given the force and the distance, and it's really easy to figure that out. So this is our equation. Again, this is on the formula sheet. You don't need to have to derive this, but it's nice to see where it comes from. Yep. Force electric. Yeah, I know. There's not enough letters in the alphabet. Hence why they started using Greek letters. I just said that. Notice there's a similarity between gravitation and electric potential. Is this the example that's next in your notes? Just to make sure. How much work is being or must be done to bring a 4 microcoulomb charge Okay, so again, here is our microcoulomb. It takes too long to search in the symbols to try and get the mu symbol, so it's just written as U, but that just means 10 to the power of negative 6. So we want to move a charged object from a long ways away to within 1 meter of a 6 microcoulomb charge. So this is what it looks like. Essentially, this is at an infinite distance. We are bringing this closer till it's now at 1 meter away from this. So obviously, this is going to require work because these are both positively charged objects. This object is fixed. This one's stationary. It's not moving. And we're just taking this charge, moving it here. How much work are we doing? Well, work is change in energy. And then in this case, we're not talking about kinetic energy. Yes, it's moving, but we're taking it from here, stationary, to here, stationary. So kinetic energy does change in the middle, but between the beginning and the end, it's staying the same. So we're only dealing with potential energy. Like always, final potential minus initial. Initials add 0. Why is the initial potential 0? What do you think? Yeah, take a look at our equation. So it's KQ1 over Q, or KQ1, Q2 over R. If R is basically at infinity, some number divided by infinity is just 0. You've seen limits before in calculus. As R approaches infinity, you're going to get it at 0. Did you just ask if limits are in calculus? You obviously haven't been paying attention in class. So we've got work is just equal to our final potential energy. We have our equation with the final distance between them. You've got your numbers, plug them in, you get 0.22 joules. So not too bad. I'll wait there for a sec so those of you doing the notes. No, 1, 2, 3, 4. 4 marks. Yep. Pardon me? 10 to the power of 9. And ignore the units in here. They like to put units. I don't know why. You don't need them in the equation. Okay. Different teachers are different. What they want. In university, you'll find different stuff. So note 2 things with this. Potential energy is a scalar. Energy is scalar, so we do not do vector addition for this.
Scalar, no vector?
Energy is a scalar. Yep.
We always use vector for energy.
Nope. If we talked about what's your potential energy, we never said it's your potential energy is this many joules up or down.
Yes, you have.
No. And this again, this is why this is confusing, because not only do we have now electric force, electric fields, electric potential energy. Now we need to deal with half of those are scalar, half of those are vector, and when they're scalars, we use plus or minus. When they're forces, we don't.
Forces is vector.
Forces are vectors. We do not use plus or minus.
Okay.
Potential energy and electric potential are both scalars, so we have to use plus or minus. So it's a nice thing that you have the ability to make your own formula sheet, and you can write that on it.
For the final?
For your final. Like I said, at some point I will show you a chart that summarizes everything really nicely. So in this case, when we're bringing our positive charge closer to a positive charge, we have to put energy into this system. There's no way that this is going to occur naturally, so we have to do work. This is different if one's positive, one's negative. You don't need to push that object to get it closer. They want to go there. So you have to actually put negative work in because you're getting energy out of the system instead of putting energy into the system. You're going to have a negative work. So you're not going to have negative potential energy. You'll have negative work. Yeah. It's your change in energy. So just like we did here. So here, where would it come into play? So when you put in your charge values here, you'd put in a negative for this, and you'd end up with a negative final potential energy.
So I put negative when the person says negative charge?
Yeah. Layla, did you have a question?
I was going to ask if the negative with another negative is like a
Yeah, you'd still have positive work because you'd have negative charges, two negatives times each other, and it'll get positive as well. This one, I think, is later on in the notes, correct? How much work is done to bring a negative?
Can I solve this one? What?
It's phrased differently. No.
Is this? Okay, good. So let's try this one. So same situation, except now we've got a positive and a negative charge. Danny, you seen?
So Brandon, why don't you ever let us to go up there and answer
Because?
questions?
It's not giving you people to
So here we are, we're moving our charge, same as the last question. We're doing the exact same thing. Work is changing potential energy. The initial is 0 because it's a long ways away. We have our equation, plug in numbers. Notice here now it's negative because I've got a negative charge. And we end up with negative work. Again, because you do not need to force this object to move over. Okay, you can think of this as if there's two people in my class that are friends, it's not very hard to force them to sit beside each other. Whereas in the last question, if I get two mortal enemies in my class and I try and force them to sit together or work in the same group, then it doesn't work out as well.
What's the result of having negative work?
So that means you do not need to put energy into this system.
It just happens on its own.
Yeah. So it's like this. It's the same as gravity. So if I want to put this water bottle up, I need to put energy into this water bottle because I'm giving it more potential energy. But if I let go, I'm not, or if I bring it down, I'm not having to do work. Gravity's doing work, I'm just slowing it down. So this bottle loses energy when it goes down because it has less potential at the end. So that's why the work is negative, because this bottle lost energy. Yep.
Is the energy based off of you or
the bottle? Because it had less potential energy, now it has more. So the change in energy of the bottle is more. So I have to take energy from myself, put it into the bottle to bring it up higher.
What if I'm pushing the bottle downwards faster than if I just like if I hold it down like this?
Gravity is still about.
I put it down, that's like my hand faster than my gravity. That's the negative.
If you are pushing downwards, I guess technically there's still a force times the distance that you're pushing downwards. but gravity is causing it to accelerate faster. But I guess technically you could have a downwards force where you are putting more energy into it, but if you're applying a force downwards, you'll have an acceleration, which means your kinetic energy is going to change because of that. So the energy that you're putting into the system causes an acceleration. So change in kinetic energy. What's that?
You use energy, you apply force, so it stays like you're pulling it down.
Yes.
So if you hold it there, you exert force, or you just gravity.
So you are applying muscles, but remember that situation where I did last year where you had someone holding a heavy object and one person with a pencil that just picks it up and down? The person with the pencil is doing more work because they're actually moving some distance. So that's different than just supporting a water bottle. So this is why it's negative. You're releasing energy, or you have a less energy than what you started with. So therefore work is negative.
Isn't it like addition and subtraction? Negative and negative give positive. Positive and negative give negative.
It's not quite just like adding and subtracting. It's just where I put the negatives in here. Okay, this one is for later. Still later. Okay, so that was potential energy. Now we need to talk about electric potential. You've actually seen electric potential before. I taught you it last year. It's voltage.
Is it voltage?
It's just voltage. Some sort of power supply. So, you've seen this before. Don't worry, we're not getting into circuits. This is our equation for electric potential. It's just the amount of potential energy per unit charge. So the amount of charge you have is kind of like the ratio between those. If we take our EP equation, plug it in, we get a new equation. No, this is voltage, which is electric potential. Voltage, yeah. The, whatever the test charge is. So think of this like, you remember with gravity, we typically dealt with if you're, let's see, gravitational field strength, we got rid of whatever the satellite was that's around it and just use the planet. This is kind of the same. If we want to figure out what's the potential, the electric potential around some charge, we don't care about what's the other charge that's around it. So this one actually does not have an equivalent in gravity. This is the only one of the four you learn in this unit that doesn't have a gravitational comparison between it.
What are alpha particles?
Alpha particles, that's just the nucleus of a helium atom. Yeah, you can just Google what the mass is and what the charge is. I won't give you something like that on the test. It's a good thing you're graduating in a month. So, electric potential is defined in terms of a moving positive charge, like everything we talk about moving positive charge. So therefore, positive charges are going to move towards low potential. Negative charges are going to move towards high potential. So remember, we're talking about electric potential, not electric potential energy. And we can actually, if we went back to circuits, we could talk about this specifically in terms of circuits. If we assume that your current is positive charges that flow, your positive charges move to a low potential, meaning it's moving towards the negative side of a battery. Well, we just talked about positive and negative charges instead of dealing with potential. So the unit for potential is joules per coulomb or volts. Coulomb from a charge, you can do it volts, doesn't matter.
Are the positive charges protons and negative charges?
Yes. In general, yes. Something can be positively charged if I lose electrons. So think about chemistry with your particles. If you have ions or you have more or less electrons, that changes it from positive to negative. You'll have to draw the diagram. Pardon me? No, you just have positive and negative ends to the battery. It's based on where more electrons are, yeah. We're not doing currents, we're not dealing with circuits. No. So, given this, always triangles, yep. So with this, here is our diagram. I've got 3 charges, and I want to know what is the potential at point P. So this is kind of like what's the electric field strength, except now we're dealing with what is the potential. Now the nice thing about this is, as I said before, electric potential is a scalar. So even though there's angles, I could care less about them. All I need to do is I need to add them like scalars instead of vectors. So that means no vector angles, no vector diagram. Just simply figure out the numbers and add them. That's all you need to do. So this is kind of nice with the potential. You just need to figure out what that value is. Again, scalar, use positive and negative. So in order to solve something like this, it's really straightforward. Figure out the potential due to charge 1 at point P. Figure out the potential from the second charge. Figure out the potential from the third. Add them all up. It's really as straightforward as that. Yeah, just hang on a sec. So we have our equation for potential. It's KQ1 or KQ over R. R is the distance between them. So this one is due to charge 1. So it's K, 9 times 10 to the power of 9, times the charge, divided by the distance. Again, distance needs to be in meters. You will often find your distances are tiny, just like your charges are tiny. And then you get the potential. So that's due to the first charge. Do the same for the second. Again, it doesn't matter that it's at an angle. I just need the distance between them. So, not for potential. There's no angles with this. Because the charges are positive. Positive, positive. This one's negative. So therefore I have a negative potential. Again, it's a scalar. There's no direction. So to get the total, just add them. So here's all 3 of our potentials. We just simply add them all together, and we get 694,000 volts. So that's a fair amount of electric potential. Because your distances are the same, are different. So that wouldn't work. So again, when you're going to come to the test, and you need to figure out which one is which, you need to be thinking about, is this a vector or is it a scalar? And then based on that, you'll be able to figure out vectors, no signs. Scalars, I put signs. Vectors, I need to add like vectors, so the direction matters. Scalars, they don't, because I'm just adding them as scalars, so I don't care about direction. I can come back to the slide if you need to write down numbers. It's not too bad. So here's where typically this would kind of be split into a separate class, but it's really not too bad. What's that? It's potential difference next. Okay. So the next part in the notes has something about equipotential lines. Don't worry about that. That never shows up on a test. It doesn't really matter. I feel like it's more like geography. So you can just skip all the way down until you get to potential difference. Yeah. Yep, because this part's going to be really short. Yes. Yeah. It basically just tells you where lines are, where there's a line, it's equal to whatever. The one in the AC in the back is working if you want to go sit back there. So if I'm looking at, or if I'm asking for a potential difference, it just means what's the difference in the electric potential between 2 points. So if I'm looking for the difference, take one, take the other, subtract. That's why this lesson's really easy to combine together. So for example, if I have 2 points, point A and point B, the difference between them is just going to be, there it is. The potential difference between A and B is just voltage at B minus voltage at A. Nothing new. I just call it potential difference. The difference between two of them is just subtracted. What's that? Depending on which one's higher. Yeah. So the potential difference between the two of them, you'll be able to figure out what value that is. And depending on which one's higher and which one's lower, you can determine the direction. So for example, if on the right I have a high potential, remember positive charges like to move to a high potential, so they'll move to the right. But the potential difference is more like an absolute value of it.
So you find this voltage in the diagram like the one where the charge is moving this way. And like that the voltage would always be higher than subtract from its line.
Yeah, so you'd be looking at the moving charge and what the potential difference between those 2 points would be. Like you'll see in a question, like this. So for example, here's 2 points, point A and point B. If I want the potential difference between those, it's just a matter of figure out the potential at point A, what's the potential at point B, subtract them. Again, just take the bigger one minus the smaller one, it doesn't really matter.
You need to just subtract the distances because the thing is the same.
If you subtract the inverse of the differences, yes. The inverse of the distance, then that works. Potential, scalar. So yes, you could factor this out, and instead of having this, you could do it as KQ, that's it, KQ 1 over RB minus 1 over RA if you really wanted to, but this just makes sense too. So this is why it's really not that bad. Again, if you want what's the total potential, add them. If you want the potential difference, subtract them. Really straightforward. Yep.
Same like the test I wrote with small young vectors, we add absolute value with respect to the
Sure. Yep. So if I had something like this and I wanted to compare these two and say, okay, which way would a positive charge go? It doesn't really make sense in this question, but you could take a look at, okay, which one's bigger? The positive charge goes to the bigger one, which makes sense because if this is a positive charge, my other positive charge doesn't want to be close, it wants to be farther away. So it's going to move towards the higher potential. It would technically just push it away. I'm just saying if it just had the path to move from here to here, you could see which direction it would go.
Would it always go in the same direction?
Yes, unless you limit its path. Yes, it would always go in the same direction. So like for circuits, it has a direct path that it has to take. So your power supply in a circuit has a potential difference, which we'll see next class. So your electron just has one path it can take, or the parallel path in a circuit, and it has to go from one end of the battery to the other. And depending on which side of the battery has a higher potential, will determine what direction it goes.
If the diagram doesn't already indicate that this is A and this is B, would we know which church is bigger by seeing which distance is smaller?
Yes. Yeah. Yeah, you can just figure out based on the distances. Since you're dividing by distances, the smaller distance has the higher potential.
When the negative charges are affecting the most people, is that like an electron goes from one atom to the other?
That's a good question. I'm not sure. It has to do, I think, more with particles and them wanting to create a complete shell or whatever layer they have for their electrons. They want to make sure that that one is complete. So they are more likely to accept an electron if they just need one more to fill their outer shell. If they just have one extra electron on the outside, they're really likely to get rid of it so they can have a... It's very unlikely that you have an electron just floating around, but you can. So this is the last question here. So this is a nice question that is very common. So we've got a point charge that is here. And, sorry, we got a 4 located at point A, stationary charge here, how much work? Okay, so this charge here is stationary. This one's fixed, it's not moving. It's stuck there. Whereas this charge is going to be doing two things. First, I'm going to take this charge and move it over here. So that's the first thing I'm going to do in part A. I want to know how much work is done moving this charge from here to here. You've seen that before. We did that in a question already. So it's simply going to be work is going to be change in potential energy. Notice this time my initial potential is not 0 because I'm not at an infinite distance. So I cannot cross out the initial potential energy. But we have equations for this. We've got KQ1, Q2 over RF minus KQ1, Q2 over Ri. You have your values here. You can plug those in. Everything stays the same except your distances. So if you plug those numbers in, you get this. Subtract them, you get this. So this is the amount of work. Our work is positive. Does that make sense in this question? Yeah, I have to put energy in because I have two positives, yeah. So this is not going to happen naturally. You have to push it.
If we have two negatives, our work will also be positive, right?
Correct, yeah. Okay. Because if you had two negatives, if you're trying to push those two things together, you're still doing work. And that would show up in the equation because this is a scalar, so we'd have a negative times a negative.
The only time we have negative work is if there's positive and a negative.
Yep. Okay. Yep. You only have negative work if you have positive and negative. Yep, that's right. So this is the amount of work. This is the change in potential energy that we have. I will leave it here a sec for those who are writing it down. Part B, what we're going to do is we're going to take this particle at point B and we're going to let go. So essentially you can think of it like this. We've taken this charge, we've forced it to go here, and then we're going to let go and see what's the speed at point A again. So can you visualize what's happening? We've got two charges, they don't like each other. I'm forcing this one to move here, and then I'm letting go and seeing what's the speed over here. Yeah, like a slingshot, like a Gauss cannon, stuff like that. This one, let's see, would be a 1, 2, 3, 4 points for this one. And then for the second part, 5, 6, 7. Yeah, this would be a 7-point question. For A and B. 4 for this one, 3 for the next. How do I what? We'll get there. So I've solved for what's the change in potential energy. Like I said, we're now going to release it and see what's going to happen. So the change in the amount of work that's done from going from A to B is going to be the exact same as letting go of B and then moving back to A. Because I'm now taking the potential energy that you gain from this. Remember, potential energy, if you reverse the action, you get that energy back. Because it's a conservative force that's acting. So we've got change in kinetic energy is the negative change in the potential. We solved for potential. We already figured out the work. So the change in the potential energy we have already. So therefore, we know what the change in the kinetic energy is. With me so far? It's like a conservation of energy question.
Isn't this equation supposed to be ordered?
Nope, this is conservation of energy. So this is just saying your initial energy equals your final. If you rearrange it so all the kinetics are on one side and all the potentials are on the other, you get this equation. So therefore, change in kinetic energy is kinetic final minus kinetic initial. It's initially at rest. So therefore, my change in kinetic energy is just equal to EKF. Solve for, what's the final velocity?
So we use that net equals the meaning of the final velocity of the acceleration.
You could, yeah. If you figured out what the net force is, so the net force would be the force electric. The problem with that is you'd have to use calculus to solve it because your distance is changing, so therefore the R value is going to change. So it wouldn't work because your force changes as it goes further away. So this one's the best way to solve it. Any questions with that? Yeah, it's in the question, part A, right before the part A, it tells you the mass of that charge. Any other questions? Okay. So that concludes this.